This week we're going to talk about linear kinetics, so linear forces, otherwise known, where we'll mostly go through Newton's 3 laws of motion and how those apply to practical situations, specifically in kinesiology. After this chapter, you should be able to explain Newton's 3 laws of motion and apply his second law of motion to determine acceleration of an object if forces acting on the object are known, and apply his second law of motion to determine net force acting on an object if, again, acceleration of the object is known. You will also be able to define impulse, momentum, and explain the relationship between these two concepts, and also describe relationship between mass and weight, although we have already gone over this content a little bit in prior chapters. Newton's first law of motion is the law of inertia, and inertia is resistance of an object to changing motion. So if there are no net external forces acting on an object, so no net external forces, that object will not move, or it will stay at rest, or it will continue moving at a constant speed in a straight line if it was already moving. So whatever presence or state an object is currently in, whether that's at rest or in motion, it will remain at rest or at a constant speed if no other external forces act upon it. Mathematically, Newton's first law states that instantaneous velocity remains constant if the sum of all forces are 0. So again, V in this concept or equation is instantaneous velocity, not average velocity, but instantaneous, and the sum of all forces is relative to the net force of all external forces. To give a practical example, this is a free body diagram of a dumbbell when it is held still in the hand. So the weight of the dumbbell here is directly equivalent and in equal opposite direction of the normal force. Interpreting Newton's first law, we know that if an object is at rest and the net external forces acting on it are 0, the object must remain at rest. If the object is in motion and the net external forces acting on it are 0 again, the object must continue moving but at a constant velocity and in a straight line. Continuing this interpretation, one component that is extremely important that you all remember is that the net external forces acting on these objects must remain 0 throughout, whether this object is at rest or in motion. Linear momentum quantifies the current state of motion and an object's resistance to change. So mathematically, linear momentum is L is equal to mv, where L is linear momentum in kilograms meters per second squared. Mass is obviously in kilograms, and instantaneous velocity is in meters per second. With conservation of momentum, in rewording Newton's first law, linear momentum is constant if, again, the sum of forces is 0. So this is useful for analyzing a group of objects, or what is otherwise known as a system of objects. And if these objects are considered together as one system, then the forces that the objects exert against each other are internal forces and do not affect the motion of the whole system. So if velocity of one object in a system increases, then velocity of another object decreases to conserve momentum. So initial linear momentum and final linear momentum have to remain equal. So if we have multiple objects within a system and one velocity goes up, right, then the other has to come down in order for them to remain equal. So elastic collisions are one in which there's no loss of kinetic energy in the collision. So for example, if we have two objects in a system, they collide head on and they separate. One, if we use the coin analogy, one coin will slow down, the other coin must speed up. So in this system, the momentum of the entire system is conserved. On the other hand, in perfectly inelastic collisions, or what's called plastic collisions, momentum is still conserved, but rather than bouncing off one another, objects in a collision stay together after the collision and move together with the same velocity. So we know that the sum of these two momentums are going to remain the same. However, instead of having two initial velocities for these two different objects, the mass of the objects will then sum together and create a new final velocity together as one system. Coefficient of restitution is defined as the ratio between the velocity of separation and velocity of approach of objects impacting one another. So we've talked about coefficient of restitution a little bit with friction, and in these next couple slides we will talk about how this is actually calculated. So velocity of separation is the difference between post-impact velocities of two colliding objects, and the velocity of approach is the difference between pre-impact velocities of two colliding objects. Coefficient of restitution is mathematically expressed as E is equal to V1 minus V2 over U1 minus U2, where E is the coefficient of restitution and V is the post-impact velocity and U is the pre-impact velocity. So coefficient of restitution is the difference in post-impact over or divided by pre-impact velocities of two colliding objects. Coefficient of restitution does have a value range between 0 and 1, okay, so it can be anything from 0 to 1. It is directly affected by materials themselves and even temperature of colliding objects. And how this really applies to exercise science and sport in particular is that certain sports have rules that specify E values to maintain integrity of a game and to maintain safety. So if you think about turf fields, there has to be a specific coefficient of restitution between the turf grass itself, whether that's the amount of little rubber pieces that's within the turf, and athletes' cleats to maintain safety. You also have coefficient of restitution rules within basketball. The E value has to be maintained within a certain range. For example, the coefficient of restitution between the bouncing ball and a court. Right, same thing with volleyball. So we've talked about coefficient in the form of friction, but if you think about it in sport, specifically relative to injury prevention, this value can be extremely important in maintaining player safety and keeping athletes from getting injured as often as they could if this value was not maintained or not specified within rules. A fairly easy way to determine coefficient of restitution, especially in a sport that involves some type of ball, is dropping this ball from a specific height onto an immovable object such as a floor, all right? And then mathematically, you would determine the coefficient of restitution by square rooting the bounce height divided by the drop height. right? So this is really incorporated into any type of sport that has a ball that has air in it, specifically football, basketball, volleyball, soccer. This experiment, or this determination of coefficient of restitution, is actually what creates rules for the amount of pressure that has to be in some type of ball in any given sport. So if you think about even Tom Brady's deflate gate when he was with the Patriots and the ball wasn't pumped up as much as it should, they probably determined how much a football should be pumped, or the amount of pressure that should be within that ball, by determining the coefficient of restitution and determining the rule for that game. That is all we have for part 1 of linear kinetics. So we will discuss Newton's second and third laws and the application of those within our part 2 component.